So to summarise, we found for our projectile launched at 13 meters per second at an angle of 40 degrees to the horizontal, the time for the projectile to reach its maximum height here is 0.85 seconds, and we've calculated that the maximum height is 3.6 meters. So if we move on to the next question, question 2 here, for the same situation where the projectile is launched initially at 13 meters per second at an angle of 40 degrees to the horizontal, calculate the flight time, or the time of flight. Well, we've already calculated the time for the projectile to reach maximum height. This time the question's asking for the whole flight time, so that's the time to reach this point here just before it hits the ground. So if we return to our original grids, you can see I've just redrawn the grids here, and remember we resolved the velocity to get the initial vertical velocity and the initial horizontal velocity. If I just take you back to this diagram here, remember this gave us our initial horizontal velocity and our initial vertical velocity. So I've just refilled in the grids here, and this time we're going to use the grids to calculate the flight time, the time of the whole flight before the projectile just reaches the ground. So what can we fill in the grid there if we're considering the moment just before the projectile hits the ground? Well, we want to calculate the flight time. Let's just think for a moment. If we return to this diagram, what can we say at this point here, just before the projectile hits the ground? Well, we'll certainly have horizontal displacement. The projectile will have travelled all the way over here relative to the start, but you can see that relative to that start point there's no vertical displacement at the moment just before it hits the ground. It has a positive displacement throughout, and at this point here we've got, relative to the start point, a zero vertical displacement. So returning to our grids here, if we're considering the time of flight, the time the projectile for it to just before it reaches the ground, we can set the vertical displacement equal to 0. So we've got 3 pieces of information in our SUVAT grid there, and 2 unknowns, the final velocity and the time which we're trying to find. So we've got S, U and A, and we're trying to calculate T. And again, if you refer back to the SUVAT equations, have to think carefully about which SUVAT equation we can use here. If we have a look at S equals ut plus a half at squared, let's try and use that one there. So if we just write down S equals ut plus a half at squared, and we're going to apply this to the vertical. Remember, it's always worth writing vertical there, just to remember every piece of information substituted into that equation has to involve vertical values. Now the moment, we're trying to calculate the moment just before it lands here, and this is to give us the time of flight, and we've got vertical displacement equals 0 just at that moment. So if we substitute 0 in here, now this time the initial velocity, the initial vertical velocity, is not 0. It's not one of those horizontal launch situations, so we need to substitute in our value here the initial vertical velocity, 8.36 times t, which is unknown, plus a half times minus 9.81 times t squared. And again, what you find is a potentially difficult equation to rearrange to find t. If you substitute the values in first and get this equation, you see, because the left hand side is equal to 0, we have a common factor on the right hand side here, t. There's a t there, and we've got t squared there, that's t times t. So if we divide the right hand side by t, we'll lose this t here, this will cancel out, we'll lose one of those t's there, and 0 divided by t leaves us 0. So the equation becomes 0 equals 8.36 and 0.5 times minus 9.81 is minus 4.9t. If we move this over to the left hand side, we get 4.91t is equal to 8.36, and so t is equal to 8.36. I'll just make my decimal points a little bit clearer on the video here. Divide by 4.91 and 8.36 divided by 4.91 gives us 1.70 seconds for our time of flight. So back in our grids there, we can add in 1.70 seconds. So that's how you can calculate your time of flight once you've filled in your values in your grid. If you recognise the vertical displacement as 0, that allows us to calculate our flight time. Now, you may have noticed here that there is a shortcut based on our previous work. If I just remind you, at the start we calculated the time it took the projectile to reach its maximum height, and we found that to be 0.85 seconds. I summarised that in a diagram just a moment ago here. It took the projectile 0.85 seconds to reach its maximum height. We calculated that first, and we also calculated the maximum height, 3.6 meters. And actually, if a projectile is launched on level ground and you ignore an air resistance, then the time to get from here to here is the same as the time to get from there to there. So if we doubled 0.85, that will give us the complete flight time, 1.7 seconds, which is what we found just a moment ago. If we hadn't calculated the time to reach the maximum height first, then we would have, in order to calculate the total flight time, we'd have to have used this technique with this value here. If we'd already calculated the time for maximum height, then we just needed to double the time to calculate the whole flight time. So often with a little bit of thought you can find shortcuts if you're a little bit careful. Well, let's ask ourselves another question then. Question 3. Calculate the final, and by final here we mean just before landing, calculate the final vertical velocity. So if we go to our grids again, let's move up to the right hand side there. The final, meaning just at that point before landing, we want the final vertical velocity v here. Well, we've already calculated t, so we have 4 values in the grid, and we've been asked to calculate the final vertical velocity here. If we hadn't already calculated t, if we had had a, u and s, then we could still calculate v, and we'd need the Suvat equation involving s, u, v and a. Just refer to the Suvat equations here. You'll see it's this one, v squared equals u squared plus 2as. So if we apply this one here, just creating some space here, v squared equals u squared plus 2as, and we're applying this vertically. V is the value that we want to find there, so v squared equals u squared, and looking at the grid, that was 8.36. We'll just refer up to the grid there. Earlier on we'd resolved our initial vertical velocity, 8.36, so we square that, and we add 2 times a minus 9.81 times s, which at landing is 0. So we find that v squared is equal to 8.36 squared. So it seems fairly straightforward to calculate v then. V is just going to be 8.36 meters per second. We square root both sides here. But we have to be a little bit careful because it could either be plus 8.36 or minus 8.36. And with a bit of thought we can see it would be minus 8.36 since the projectile is going to be moving downwards. So if we return to our original grid, we've now got the final vertical velocity 8.36. Look familiar? Well, the initial vertical velocity was plus 8.36, and we've got the final vertical, just before landing, vertical velocities minus 8.36. And if we just look over at this diagram here, that makes sense because the projectile is being launched on level ground. Just think of a simpler scenario where you throw a ball directly upwards. If a ball leaves your hand at 5 meters per second, it'll travel upwards, stop momentarily, and return down. And if there's no energy loss due to air resistance, then the ball will return vertically down into your hand if your hand's at the same height, with exactly the same velocity as it left your hand from. We've got a similar situation here. If we take this initial velocity here, we could break that down into two components. Remember, we broke down our initial velocity into a horizontal and vertical component, and repeating what we did earlier, we found plus 9.96 meters per second was the original horizontal velocity, and plus 8.36 meters per second was the initial vertical velocity. Well, because the projectile is launched on level ground, what we find at landing is the situation is the horizontal velocity remains constant throughout, since there's no horizontal acceleration. We've found that the vertical velocity is the same in value, but it's negative since the projectile is moving downwards, so we have minus 8.36 meters per second. We don't really need the minus on the diagram here since we've shown the arrow coming downwards. And if we recombine those like we did in the part 1 video to get the overall velocity, well, what you'll see is these two sides are the same here, it's just this one's downwards. So actually the overall velocity on landing, you could use Pythagoras theorem if you want to confirm it to yourself, is 13 meters per second, which is the same as the original overall velocity at launch. And the angle, instead of being 40 degrees above the horizontal, will be 40 degrees below the horizontal. So again, there's a shortcut here. If you'd recognise that, if you'd recognised it's a projectile being launched on horizontal ground, then in our grids we could have filled this in straight away, that at the moment when it lands, the final vertical velocity will be the same in value as the initial vertical velocity. It'll just be a minus sign. Now that's only true at the moment that just before it lands, if the projectile's on level ground. It's not true at all times. Obviously at maximum height, the vertical velocity, if you remember, is 0. So this is only true just before the projectile lands, but it's a useful shortcut to know. And similarly, you need to know that the vertical displacement is 0 at the moment just before it lands. And that gives us these 4 values here, which will quickly allow us to calculate the flight time. So you could have actually started with this one or this one in order to calculate the flight time. Remember, below here we put s equals 0, but equally we could have just straight away put minus 8.36 at the moment just before it lands, since the projectile is on level ground, it's being launched on level ground.